Alright, so now for part 2, what we're going to be looking at is how to differentiate exponential functions, logarithmic functions, alright, and the natural log function. So we need to know how to differentiate these type of functions. So again, just like when we were doing differentiation 1 from unit 1, we had to learn particular rules. We're going to have to learn some rules to differentiate these types of functions. So for example, if y is equal to some exponential e to the f of x, if y is equal to e to the f of x, then dy by dx, which is the derivative, dy by dx is equal to f prime of x times e to the f of x. That's how we differentiate exponential functions. Example, let's say y is equal to e to the 3x minus x squared. If y is equal to e to the 3x minus x squared, then dy by dx is equal to, how do we differentiate 3x minus x squared? It's f prime of x, this is your f of x, and so the differential of 3x minus x squared is 3. When we differentiate 3x, we get 3 minus 2x times e to the f of x, which is times e to the 3x minus x squared. Alright, now let's say we were given y is equal to e to the sine x plus x squared. How do we differentiate sine x? And so then dy by dx would be equal to, when we differentiate sine x, we get cosine x, plus when we differentiate x squared, we get 2x. So we get cosine x plus 2x e to the sine x plus x squared. And that's how we differentiate this function. Alright, so that's the rule for when we're differentiating exponential functions. So remember, if y is equal to e to the function of x, then dy by dx is equal to f prime of x, which is the derivative of f of x, times e to the f of x. Now, let's look at differentiating log functions. Let's start with the natural log known as ln. So on your calculator, there is 2 logs. You'll see one right here that says ln, that's ln, natural log, and then you have log to base 10. Alright, so now we're going to be looking at log functions, and we're starting with the natural log, which is ln. That's log to base e. So if y is equal to ln, a function of x, then dy by dx is equal to f prime of x divided by f of x. That's it. If y equal to a log function of x, then dy by dx is equal to f prime of x over f of x. So an example is, let's say y is equal to ln sine 3x. So this is your f of x, sine 3x. So then dy by dx is equal to, when we differentiate sine, what do we get? When we differentiate sine 3x, we get cos 3x times 3. So this becomes 3 cos 3x divided by our f of x, which is sine 3x. Now you can leave this answer like this, but the main issue is watch here. Cosine over sine is cot. And so we can write this answer as 3 times the cotangent of 3x. And so that's how we would differentiate y equal to ln sine 3x. Now, let's say I had given you that y is equal to ln, so y is equal to ln tan e to the x. So y is equal to ln tan e to the x. So if y is equal to ln tan e to the x, then let's find dy by dx. So let's write it down. Y is equal to ln tan e to the x. And so dy by dx is equal to the differential. We need to differentiate tan e to the x first. When we differentiate tan, we get sec squared e to the x. But then we have to multiply it by this thing right here, and the differential of e to the x is e to the x. So I have to multiply it by the differential of what is e to the x, and the differential of e to the x is just 1, or multiply it by 1. Alright? Then now we're going to divide it by tan e to the x. And so the derivative is just sec squared e to the x over tan e to the x. So that's how we differentiate log functions. So the derivative of ln f of x is f prime of x over f of x. Alright, so that's how we differentiate log to base e. Now let's say we're differentiating log to base a. How would we differentiate log to base a? So let y is equal to log to base a of x. How are we going to differentiate this function? Now we know how to differentiate ln function, but I don't know how to differentiate this function, right? We don't know how to differentiate this function. So what we can do is use change of base. We're going to use change of base to change the base to base e. So recall that log to base e of x is equal to ln x. So we're going to have to change this base. And so we can change this to, this can be used change of base law, where we can write this is now log to base e of x over log to base e of a. So this is y. So now we can then go ahead and differentiate this, because then this is now equal to log to base e of x is ln x over log to base e of a is ln a. Now ln a is just a constant. Ln a is just a constant. A is just a constant. And so this becomes y is equal to 1 over ln a times ln x. And so dy by dx is equal to 1 over ln a times the differential of ln x, which is 1 over x. And that's how we differentiate this. So the derivative of log a to the x is 1 over ln a times 1 over x. And that's how we differentiate log a to the x. So let's use an example. Let's say I ask you, given that y is equal to log to base 5 of 3x squared. So differentiate this function. First you need to do is write this as, this can be written as ln 3x squared divided by ln 5. And so that's equal to 1 over ln 5 times ln 3x squared. And so now all we have to do now to differentiate this now, we get dy by dx. dy by dx is then equal to 1 over ln 5, 1 over ln 5 times the derivative of ln 3x squared is, so this is ln f of x, and to differentiate ln f of x, it is f prime of x over f of x. F prime of x is the differential of 3x squared, which is 6x divided by 3x squared. And so it works out to be, we can simplify this, x over 3x squared. So 6x over 3x squared, 6 over 3 is 2, x over x squared is x. So it works out to be 1 over ln 5 times 2 over x. And that's dy by dx. That's how we differentiate this log function. Alright. Now the next one we're going to look at is differentiating a to the power x. So let's say I give you y is equal to a to the power x. If y is equal to a to the power x, how are we going to differentiate this function? Well, I don't know no rule that can differentiate this function, but if y equal a to the x, I can take the log of both sides. So this then tells me that if y equal a to the x, then ln y equal to ln a to the x. Now if ln y is equal to a to the x, then what I can do is I can say, alright, I can use rules of logarithm that then tell me that ln y is going to be equal to x ln a. X ln a. So ln y is going to be equal to x ln a. Alright, x ln y. Ln y is going to be equal to x ln a. Now I'm going to have to differentiate both sides. Alright. Now when I differentiate y, when I differentiate ln y, I'm going to get 1 over y, but I'm differentiating y with respect to x, and so I have to write dy by dx. So it is 1 over y times dy by dx. Think about it this way. When y equal f of x, when you differentiate y, what we get dy by dx. And so when you differentiate ln y, you're going to get 1 over y times dy by dx. We look more at this when we're doing implicit differentiation. Alright. Then this is going to be equal to, when you differentiate x ln a, you just get ln a. And so if you multiply this equation through by y, we get dy by dx is equal to y ln a. But then what was y? Y was a to the x, and so dy by dx becomes a to the x ln a. That's dy by dx. Alright? dy by dx is a to the x ln a. So let's look at an example. Let's say y is equal to, let's say y is equal to 4 to the x. If y is equal to 4 to the x, then what happens is dy by dx is going to equal to 4 to the x, which is a to the x ln a, which is ln 4. So it's 4 to the x times ln 4. That's dy by dx. Easy. Soft. Alright. Now, of course, with differentiation, you're going to get a combination of all of these things. You're going to combine trigs, they're going to combine everything together, right? And so, always look out for a question where have all of them combined in one. Now, before we look at a combination of questions, let's look at inverse trig functions, right? We have to look at inverse trig functions. So let's say y is equal to sine inverse of x. And we want to find dy by dx. So if y is equal to sine inverse of x, what are we going to find dy by dx? Now look at this. I'm going to recall something that we'd have learned from grade 10 or grade 9 when we're doing trigonometry. Remember when we said that sine 30 equals 0.5, right? Sine 30 equals 0.5, and so therefore the sine inverse of 0.5 is 30. Remember that? So consider this to be y. If you were to call this 30 y, right? And this 0.5 your x, then what we're saying is if sine inverse of x equal y, then sine y equal x. So what we can say from here then is that the sine of y is equal to x. So this implies the sine of y is equal to x. Alright, so sine 30 equals 0.5. Sine inverse of 0.5 is 30. Now how do we differentiate sine y? Now this again is implicit differentiation, which we're going to touch up right after we do these. Is when we differentiate sine y, this is how we differentiate sine y. When we differentiate sine y, we're going to get the cosine of y, because when we differentiate sine we get cos. But anytime you differentiate y, just write dy by dx. So now we get cosine y dy by dx equal, or differentiate x, we get 1. Now look what I'm going to show you now. Now remember this identity from trigonometry, sine square x, or let's say sine square y plus cos square y equal 1. That's our identity from trigonometry. And so what we get then is cos square y is equal to 1 minus sine square y, and so cosine of y is equal to the square root of 1 minus sine square y. Right? That's cosine y. But then, what was y? We said that sine y equal x, and so sine square y is going to be x squared. Sine y equals x, and so sine square y will be equal to x squared. And so cos y is then equal to the square root of 1 minus x squared. That's cos y. And so right here, what we end up get is dy by dx cos y, which is the square root of 1 minus x squared, dy by dx is equal to 1. And so dy by dx is equal to 1 over the square root of 1 minus x squared. So if y is equal to sine inverse of x, then dy by dx is 1 over the square root of 1 minus x squared. So what is the general rule? So this is the final answer. So the general rule, so this is the general rule now. We're generalizing. So if y is equal to sine inverse a function of x, then dy by dx is equal to 1 over the square root of 1 minus that function of x squared. So it's equal to the square root of, we write it a little larger, so it's equal to 1 minus that function of x squared, square rooted, times in the numerator f prime of x. And that's how we find dy by dx when y is equal to sine inverse of x. So let's do an example. So let's say, for example, let's say y is equal to sine inverse of 3x minus 1. if y is equal to sine inverse of 3x minus 1, then dy by dx is equal to 1 over the square root of 1 minus x, f of x squared. Here f of x is 3x minus 1, so it is 1 minus 3x minus 1 squared times here f prime of x. Now f prime of x is, when you multiply this by 3, because the differential of 3x minus 1 is 3, so the final answer is 1. 1 times 3, which is 3, over the square root of 1 minus 3x minus 1 all squared. That's your dy by dx. So dy by dx is 3 over the square root of 1 minus 3x minus 1 all squared. That's how you differentiate sine inverse of x. Alright, now let's look at differentiating cosine inverse of x, then tan inverse of x. And we do a similar way for both of them. Now, let's say that y is equal to, cosine inverse, let's say y is equal to cosine inverse of, f of x. So then, dy by dx, or we're going to find dy by dx. So if y is equal to cos inverse of f of x, then cos y is equal to f of x. Now if cos y is equal to f of x, then when we differentiate cos, we get minus sine y dy dx. We differentiate y, you always put back a dy dx, and that's equal to, when you differentiate f of x, we get f prime of x. Alright, and again, let's recall sine square y plus cos square y equal 1. And so sine y is equal to the square root of 1 minus cos square y. But then cos y is f of x, and so cos square y is going to be f of x squared. So this becomes 1 minus f of x all squared. Alright, because cos y is f of x. And so this part becomes minus sine y, which is the square root of 1 minus f of x all squared. And that's equal to f prime of x. And I left off the dy dx right here. dy by dx, that's equal to f prime of x. Alright, now all we need to do now is make dy by dx the subject. So dy by dx is equal to, divide by this side right now to get f prime of x, divided by, we'll put the minus in the numerator, divided by 1 minus f of x all squared. That's dy by dx. dy by dx is minus f prime of x over the square root of 1 minus f of x all squared. That's dy by dx. Alright, so let's look at an example. So you have to write it down and study these rules. So let's say now y is equal to sine inverse of, y is equal to cosine inverse of x over 3. Let's say y is equal to cosine inverse of x over 3. So then dy by dx is equal to f prime of x, which is the derivative of x over 3, is 1 over 3. That's divided by the square root of 1 minus f of x, which is 1 minus x over 3 all square. In general, we don't like to leave things as fraction like this, right? 1 over 3 over 1 minus x over 3 all square. So now let's use our knowledge of surds to simplify this. So we're going to simplify it. So this becomes 1 over 3 divided by the square root of, this is now 1 minus x squared over 3 squared, which is 9. Right? Now I can rewrite this one as 9 over 9. I can rewrite that one as 9 over 9. So you're wondering, why would I rewrite that as 9 over 9? Why am I doing that? You're going to see. I'm then going to factorize out 1 over 9 from the denominator right here. So right here now, I end up get equal to 1 over 3 over, I factorize out 1 over 9 to get the square root of, factorize out 1 over 9, I get into 9 minus x squared. Because I factorize out 1 over 9 from this right here now. So then I can rewrite this again as 1 over 3 divided by the square root of 1 over 9. So I'm going to have now the square root of 1 over 9 times the square root of 9 minus x squared. Now what's the square root of 1 over 9? That's just 1 over 3, right? The square root of 1 over 9 is just 1 over 3. And so this 1 over 3 is going to cancel this 1 over 3. And so what we end up get is 1 over the square root of 9 minus x squared. And so the derivative of cosine x over 3 works out to just be 1 over 9 minus x squared. And so that's how we simplify it, and that's how we differentiate cosine inverse. Now finally, let's look at tan inverse. So let's look at y equal tan inverse. So we have y is equal to tan inverse. Y is equal to tan inverse of a function of x. And we want to find dy by dx. So first thing is, if y is equal to tan inverse of function of x, then tan y is equal to f of x. Now if tan y is equal to f of x, then when we differentiate tan, we get sec square y. Then anytime you differentiate y, you just write dy by dx. And that's then equal to, when we differentiate f of x, we get f prime of x. When you differentiate f of x, you get f prime of x. Now, here's the key thing now. Now, we have to recall this identity. 1 plus tan square y is equal to sec square y. We have to recall that identity. 1 plus tan square y is equal to sec square y. Now, since 1 plus tan square y is equal to sec square y, what we then have is that now tan y is f of x, and so tan square y is really 1 plus f of x. Remember, 1 plus tan square y is sec square, and so 1 plus tan square y is f of x, so this is 1 plus f of x all square. So that's what we get for sec square y. So we can replace that right here. So we can replace sec square y with 1 plus f of x all square. 1 plus f of x all square dy by dx is equal to f prime of x. So we can divide through by 1 plus f of x all square to get dy by dx is equal to f prime of x divided by 1 plus f of x all square. So that's dy by dx. So if y is equal to tan inverse f of x, then dy by dx is f prime of x over 1 plus f of x all square. So let's look at an example. Let's look at an example. Let's say now, look at the example. So let's say y is equal to, let's say y is equal to tan inverse, y is equal to tan inverse of x squared plus 1. If y is equal to tan inverse x squared plus 1, then dy by dx is equal to f prime of x. When we differentiate x squared plus 1, we get 2x over 1 plus f of x all squared. 1 plus your f of x is x squared plus 1, then it says all square. And that's your dy by dx. Easy question. And that takes care of inverse trig functions. The next thing that we want to look at is implicit differentiation. So notice that whenever you differentiate y, you always write dy by dx. Now we're going to get into implicit differentiation. Why do we do that? Now it really stems from chain rule. So I'm going to show you now. Now consider this. What is d by dx? D by dx of x squared. D by dx of x squared is equal to 2x, right? And so in other words, if y was equal to x squared, then this implies that dy dx is 2x. Because we differentiate y in terms of x. Now, what if I ask you to find d by dx of 3y squared? You're going to say, huh? How you find d by dx of y squared? Because this don't even write in terms of x, don't it? So how we are going to do that? How to differentiate this with respect to x when it don't even write in terms of x? Well, that's simple. Now to differentiate this now with respect to x, right? Look what we're going to be doing. It's equal to, so look what we do now, you know. Look what we do. So we're going to differentiate this with respect to x, right? So we want to find d by dx of this thing. Think of this thing as a L. So all of this was just L. So this thing right here was a L. So you want dl by dx. To find dl by dx, it would be dl by something. We can write dy times dy by dl. Agreed? If this was a L, if 3y squared was a L, then it is dl by dy. Wait. Not dl by dy, dl by dx, sorry, dl by dx times dy by dx by dl. Alright? So if this was a L, dl, so on dl by dx, so this one should be dx, and this should be dy. Nice. So the chain rule now, look what would pretty much say. This dy cancels this dy, right? And so dl by dy times dy dx, well, this dy cancel this dy and we'll still get back dl by dx. And so clearly, what we're pretty much saying then is that to differentiate now, let's remove the L. To differentiate 3y squared, it's differentiate this with respect to y. So differentiate this with respect to y, we carry down the power to get 6. We subtract 1 from the power to get y times dy by dx. We don't know what that is, so just write it down. Dy by dx. And so when we differentiate 3y squared, we're just getting 6y dy by dx. And so that's all is implicit differentiation. This is known as implicit differentiation. This is implicit differentiation. So that's all that is. So this is just implicit differentiation. That's all is implicit differentiation. So let's look at some examples. So what I'm saying now, example, let's say find dy by dx for, find dy by dx for, let's say I say xy plus e to the 3x equal 1. And I'm asking for find dy by dx for this equation. To find dy by dx for this equation, it's very simple. Look what we do now. To find dy by dx, it's going to be, this is a product, so we're going to use product rule. So remember product rule. uv, it's uv, udv plus vdu, so that's product rule. So we're going to use product rule to differentiate this. Alright, so first thing is write back the equation xy plus e to the 3x equal 1. Alright, and then now they can ask you to, find dy by dx. So we're going to differentiate both sides with respect to x. So d by dx of both sides. When I differentiate the left hand side with respect to x, what I'm going to get is keep the first, then differentiate the second, and then differentiate y, I get dy by dx, plus keep the second, which is y, times the differential of the first, which is 1. Plus, when I differentiate e to the 3x, it's going to equal to 3e to the 3x. And that's equal to, differential of 1 is 0. So all I need to do now is make dy by dx the subject in this. So to make dy by dx the subject in this, what I'm getting then is x dy by dx, that's equal to, bring over everything to the other side, so I'm getting minus y minus 3e to the 3x. So all I then need to do is divide both sides by x. So let's divide by x now, and I get dy by dx is minus y minus 3e to the 3x divided by x, and that is dy by dx. Alright, now typically the most common types of question they'll ask with this is give you some equation and then ask you for the equation of the tangent at a particular point, or ask you for the equation of the normal at a particular point, right? And so you have to get used to doing implicit, because we're going to use it in order to find the gradient of the tangent, and then we can use the gradient of the tangent to find the gradient of the normal at that point. So let's do an example. So before we do the example, let's just write down something, right? So dy by dx at the point where x is equal to a, that is equal to the gradient of the tangent at x equal a. This t stands for tangent, this t stands for tangent. So dy by dx when x equal a, is the gradient of the tangent at x equal a. And so, now the gradient of the normal, this n stands for normal, the gradient of the normal is minus 1 over the gradient of the tangent. Now this is all that we're going to use in order to be finding equations, right? In order to find equations of tangents and normals. So example, given the curve x squared e to the 3x plus 4y is equal to 2x minus 1, find the equation of the tangent and normal when x equal 1. So this says, given the curve x squared e to the 3x plus 4y is equal to 2x minus 1, find the equation of the tangent and the normal when x is equal to 1. So to find the equation of the tangent and the normal, we're all good, right? We're all good. So look at it now. So this is the curve. So we have the curve x squared e to the 3x plus 4y is equal to 2x minus 1. So we're going to differentiate both sides with respect to x. So I like to put a bracket around it and then write d by dx. This means differentiating with respect to x all of this. So to differentiate x squared e to the 3x, it's going to be using product rule, keep the first times the differential of the second, which is 3e to the 3x, plus keeping the second, which is e to the 3x, times the differential of the first, which is 2x, plus, that's product rule. Remember, product rule is u dv plus v du. That's product rule. So u dv, this is your u dv, this is v, so this is dv, plus v du, this is v, and this is du. Plus, when I differentiate 4y, I get 4 dy by dx, and that's equal to, when I differentiate 2x, I just get 2. So now I just need dy by dx on one side. And so what I'm getting then is dy by dx is equal to, now dy by dx is going to be equal to, dy by dx is equal to, so I bring over everything over to that side to get 2 minus, bring over this right here, 2 minus x squared minus 3x squared e to the 3x, and bring over this to be minus 2x e to the 3x. And then remember, this is 4 dy by dx. So all I need to do now is divide both sides by 4. So I'm going to take the 4 from here and let's put a divide by 4. So I divide it by 4. Now the next thing I need now is to find, alright, so dy by dx is this. So now, remember, we're finding the equation of the tangent and the normal. So I'm going to erase the question, but remember, give us this curve and ask us to find the equation of the tangent and the normal. So I'm going to erase, let me take off this part. So now that we find dy by dx, now that we find dy by dx, we can plug in when x is 1. So when x is 1, the gradient of the tangent, which is dy by dx, is equal to, gradient of the tangent, which is dy by dx, is equal to 2 minus 3 times, when x is 1, we put 1. 3 times 1 squared, e to the 3 times 1, which is e cubed, minus 2 times 1 times e to the 3 times 1 divided by 4. And so the gradient of the tangent is working out to be, 2 minus 3e cubed minus 2e over 4. So we're getting that is equal to 2 minus, alright, just for simplicity, I'm going to change this question from x equal 1 to x equals 0, just for simplicity, when x equals 0. So change the x equal 1 to x equals 0 for simplicity. Remember, this example I made up off the top of my head. And so this becomes 2 minus 3 times 0 is 0, 2 times 0 is 0, so this becomes 2 over 4, and 2 over 4 is a half. So that's the gradient of the tangent. So if the gradient of the tangent is equal to a half, this implies that the gradient of the normal is negative 2. As the gradient of the tangent is equal to minus 1 over the gradient of the normal, and so the gradient of the normal is minus 1 over the gradient of the tangent. So the gradient of the normal is negative 2 if the gradient of the tangent is a half. So now all we need to do is find the equation of the tangent and the equation of the normal. Now remember, let's write it down, because I'm going to take off here. The gradient of the tangent is equal to a half, and the gradient of the normal is negative 2. So that's what we have. So now for the equation of the tangent. Equation of the tangent, this is the equation of the tangent. So this means equation of tangent. T stands for tangent. Equation of tangent. Equation of the tangent is y minus y1 is equal to the gradient of the tangent into x minus x1. Now x1 is the x value that we know, which is 0. Now we don't know the y coordinate, then just tell you what's the x coordinate. But we know that it must satisfy the equation of this curve, so we can go ahead and find y. So if x is 0, this implies that if x is 0, when you put in 0 here, you get 0 times e to the y, which is 0. So we're getting 0 plus 4 times y. 0 plus 4 times y is equal to 0 minus 1. And so that is telling us that 4y equal negative 1, and so y equal minus a quarter. So if y equal minus a quarter, we get the equation of the tangent is y minus minus a quarter. Minus and minus become plus, so we get y plus a quarter is equal to the gradient of the tangent, which is a half, into x minus 0. So that would be the equation of the tangent. Now you can go ahead and make y the subject if you may. So make y the subject, we would get y is equal to a half x minus a quarter. That's the equation of the tangent when x equals 0. Now let's say we want now the equation of the normal. So we take this down, that's the equation of the tangent. The equation of the normal. So the equation of the normal will be given by y minus y1 into the gradient of the normal into x minus x1. So this becomes y minus y1, which is minus a quarter, so it becomes plus a quarter, and that's equal to the gradient of the normal, which is negative 2, into x minus 0. And so what we're getting is y is equal to negative 2x minus a quarter. And that would be the equation of the normal. So this is how we use implicit differentiation to find the equation of tangents and the equation of the normals. They're always going to ask you for that, to find equation of tangent, equation of normal. Alright? Easy stuff. Alright. The next thing we're going to be looking at now is what's known as parametric differentiation. Now, parametric differentiation. What is parametric differentiation? Parametric differentiation thus involves differentiation with a third variable. So sometimes you may not be given a function y in terms of x. Let's say I give you a function y in terms of t and x in terms of t. And then I want dy by dx, right? And so now I did not give you y in terms of x, right? And so in order to find dy by dx, we're going to have to connect them with the connector, which is the third parameter, which is the parameter t. So let's write that down. It sounds complex, but it's easy. So let's write that down. So this is parametric differentiation. So parametric differentiation, right? So here's parametric differentiation. So let's say we have y is equal to a function of t, that's y, and x is equal to another function of t, right? Y is equal to f of t and x is equal to g of t. Then dy by dx is equal to, dy by dx is simple. Dy by dx is just going to be equal to f prime of t divided by g prime of t. How did we get this? How did we get this was, first and foremost, let's look at y. If y is equal to f prime, if y is equal to f of t, then dy by dt is going to be equal to f prime of t. Now x is equal to g of t, and so dx by dt is equal to g prime of t. And so now, if I wanted dy by dx, then we're going to use chain rule again. Connect it. We're going to use chain rule. And so for chain rule, right, then what we get is dy by something, that something is t, dy by dt times something by dx. Now that something is going to be dt. Right? Makes sense, because if I cancel the dt's, then I still get that dy by dx is dy by dx. So dy by dt times dt dx gives me back dy by dx. But then what's dy by dt? Dy by dt is f prime of t. So that's f prime of t times dt by dx. But what's dt by dx? Dt by dx is g prime of t. Dt by dx is g prime of t. Dt by dx is g prime of t. And so dt by dx, so dx by dt is g prime of t. So dt by dx is 1 over g prime of t. And so this works out to be f prime of t over g prime of t. Easy. So let's look at an example. So here's the example I'm going to give now. Example. So the example is, let's say y is equal to sine 2t. Y is equal to sine 2t minus 3, and x is equal to y is equal to sine 2t minus 3, and x is equal to cosine 2t plus 4. And then find dy by dx. Find dy by dx when x equal. Find dy by dx when x equal, not when x, when t equal pi by 2. So find dy by dx when t equal pi by 2. Now first and foremost, we're just going to write that dy by dx is equal to the differential of y with respect to t. So it's equal to dy by dt. So dy by dx is equal to f prime of t over g prime of t. So this is our, well, since we never call it an f, so it's equal to y prime of t, because that's our y of t, and divided by x. So it's equal to y prime of t over x prime of t. So that works out to be, we differentiate sine 2t. What we get is, when we differentiate sine, we get cosine. So we get cosine 2t times 2. And we divide it by x prime of t. When we differentiate cos, we get minus sine. So we get that it's equal to minus 2 sine 2t. And then cosine 2t over sine 2t is cotangent 2t. So it's equal to cot 2t, and it's minus cot. It's minus the cotangent of 2t. Now when t equal pi by 2, when t is pi by 2, so when t equal pi by 2, it implies that dy by dx is equal to t as pi by 2, pi by 2. Pi by 2, 2 times pi by 2 is pi. So the cotangent of pi, remember the cotangent of pi is 1 over tan. So this is really asking us for dy by dx is just minus 1 over tan pi. Tan pi, which is a tan of 180. What's a tan of 180? Tan 180 alright, and so what we're going to get is that this is undefined. So the gradient right here is undefined, because we're going to get tan 180 is 0, but we cannot find, since tan 180 is 0, then minus 1 over 0 is undefined. So the gradient here is undefined. Right, so remember, I made it up off the top of my head why this one is undefined. So that's how we find dy by dx using parametric differentiation. The next thing we're going to look at shortly is known as partial derivatives. Partial derivatives. So you may be tempted to ask, what is partial derivative? Well, what is partial derivative? Well, partial derivatives is when we're going to find the derivative of a function with respect to one variable and hold the other variable constant. That's partial derivative. Alright? So, for example, we're given a function in terms of 2 or 3 variables. We cannot differentiate the function strictly in terms of x or strictly in terms of y, both of them at the same time. So we have to differentiate it one variable, then by another. So consider this. Consider a function f of xy is equal to x squared minus y squared plus 2xy. Right? Now, I cannot ask you for f prime of xy. That don't make no sense. No. So this function is a function written in terms of two variables, in terms of x and y. And so this would be, if we're going to sketch this graph, it would be in a three-dimensional space where we'd have our x-axis, our y-axis, and then our f of xy axis, which is the output. So we have two inputs and an output. So of course, you have what is then known as first partial derivative. The first partial derivatives are given by, so we have first partial derivatives. First partial derivative is given by, so this, it means di f upon di x. This means we differentiate the function with respect to x. So we differentiate with respect to x, and y is constant. So that's di f upon di x. Then we have di f upon di y. This means we differentiate with respect to y, and x is constant. So we differentiate with respect to y, and x is constant. These are known as the first partial derivatives of our function f of xy. Alright, the next thing that we have is second partial derivatives, and there are four of them. So then now we have the second partial derivatives. So the second partial derivatives are given by the second partial derivatives. The second partial derivatives are given by dou 2f upon dou x squared. What this means is d by dou x of dou f upon dou x. So this is just, we're going to differentiate x. So we'll find the first partial derivative, then we differentiate it again with respect to x. So that's dou 2f upon dou x squared. Then we have dou 2f upon dou y squared. So this one is thus dou by dou y of dou f by dou y. Alright. Now the third one is given by dou 2f upon dou x dou y. This is the third one. Dou 2f upon dou x dou y, and this is equal to dou by dou x of dou f upon dou y. And then finally, the last one, IV, is dou 2f upon dou y dou x. This is equal to dou by dou y of dou f upon dou x. Alright? And that is that. Alright. So these are all our second partial derivatives. So now let's look at them in an example. It's always easy when we see them in a practical example. So again, I'm going back. Oh, one final thing about second partial derivatives is this is the most important thing you need to know about second partial derivative. Now, if if dou 2f upon dou x dou y is equal to dou 2f upon dou y dou x, then f of xy is continuous. Then the function is continuous. Let's not even say f of xy. Let's just say then f is continuous. Because the function might even be f of xyz. So then f is continuous if dou 2f upon dou x dou y is equal to dou 2f upon dou y dou x. So let's look at an example with these now. So example f of xy is equal to x squared plus y squared minus 2xy. And I'm going to find all the partial derivatives. So for the first partial derivative I, then dou f upon dou x is equal to, dou f upon dou x will be equal to, differentiate with respect to x, so differentiate x squared we get 2x, or differentiate y squared we get 0, because y squared is now a constant. So now this y is a constant, and so it's pretty much like we're differentiating minus 2x. When we differentiate minus 2x, we get minus 2, and then we'll put back our y, so we get minus 2y, which is 2x minus 2y. And then now, part 2, we can find dou f upon dou y. Dou f upon dou y is, we differentiate the function with respect to y. So differentiating x squared we get 0, because x squared is now a constant. You know, we differentiate y squared we get 2y. You know, we differentiate minus 2xy, x is a constant, so we get minus 2x. So this works out to be 2y minus 2x. So that's dou f upon dou y. Alright. So now the third one, is to find, let's say we're doing the second partial derivative now, to find dou 2f upon dou x squared. Now dou 2f upon dou x squared, that would be dou by dou x of dou f upon dou x. So we're pretty much differentiating dou f upon dou x, which is differentiating 2x minus 2y. When we differentiate 2x minus 2y, we differentiate 2x and we get 2, so this is equal to 2. We differentiate minus 2y, y is held a constant, so we get 0. So part 4, now we're going to find dou 2f upon dou y squared, that's equal to dou upon dou y of, that's equal to dou upon dou y of dou f upon dou y. That's equal to, we differentiate this now and we're going to get 2. Now, finally, let's find now dou f upon dou y dou x. So 1. So let's find now dou f upon dou x dou y. So dou f upon dou x dou y, that's equal to dou upon dou x of dou f upon dou y. So that's equal to dou f upon dou y. We said that dou f upon dou y was 2y minus 2x. So we're finding dou x of 2y minus 2x. So differentiate this now. Dou by dou x of this is equal to 2. Now let's find dou f upon dou y dou x, that's equal to dou upon dou y of dou f upon dou x. And so that works out to be dou by dou y of dou f upon dou x is 2x minus 2y, which works out to be equal to 2. Now remember what we said. If dou f upon dou x dou y is equal to dou f upon dou y dou x, then f is continuous. So when we finish this question, we could also just tell them that since dou f upon dou x dou y is equal to dou f upon dou y dou x, which is equal to 2, then f is continuous. So since dou f upon dou x dou y is equal to dou f upon dou y dou x, and they're equal to 2, then f is continuous. And so now we conclude that f is continuous. And this takes care of differentiation 2. Alright, so next week we're going to be looking at integration. Alright, easy, soft.